I'm Kevin Moon, an assistant professor in data science at Utah State University. In this video, I will share with you a little bit about my research program here. We live in an era of big data. Nearly every field is acquiring thousands of samples with many dimensions, including in space applications, biology, finance, and many other areas. With this complex data, there is a need for methods that can extract and analyze information from them in relevant ways. Many existing methods simply aren't sufficient for a lot of this data, especially biomedical data. Thus, this is the goal of my research, to develop new data analysis methods for analyzing and extracting this information from these large, complex data sets. To develop these methods, I use a variety of techniques, including methods and principles from manifold learning, deep learning, machine learning in general, information theory, density estimation, and nonparametric estimation theory. I'm working on a variety of different problems in data science. This includes developing accurate nonparametric estimators of information theoretic measures such as entropy, divergence, and mutual information. These measures have a lot of different applications in machine learning and data science, such as anomaly detection, data compression, feature selection, clustering, and extending machine learning applications to probability distributions as features. I also work on developing new dimensionality reduction-based data visualization tools that preserve both local and global information using manifold learning and deep learning techniques. Other problems I'm working on include benchmarking classification performance in both the supervised and semi-supervised setting, using information geometry techniques to eliminate all sources of noise in data, imputing missing measurements in extremely noisy biological data, and using random forests to help train neural networks. Some of these projects involve deep theoretical work, such as the problem of estimating information theoretic measures, and all of them involve extensive experiments. In addition to these methods-based projects, I've worked with a lot of different kinds of data, including with radar images, solar images, neural data, biomedical data, as well as financial data, ecological, and SAR navigation data. So my research program includes a good mix of both real-world applications and methods development work. I want to briefly highlight some of the data analysis methods that I have developed, starting with the problem of data visualization. Humans are generally very visual, which means that we need good data visualization tools to help us truly explore the data. This is helpful for us to develop an intuitive understanding of the data structure and then generate hypotheses for further scientific exploration. Unfortunately, many existing visualization methods focus on preserving either local or global relationships between data points. This led me to develop a method that we call FATE, which is a visualization method that preserves both of these relationships. As an example of where we applied FATE, we measured single-cell RNA sequencing data from embryoid bodies over a 27-day time course. The data contained about 31,000 cells and more than 17,000 genes in each cell. So it's a very high-dimensional and large data set. Applying FATE to this data gave us this visualization here. We see that at the beginning of the time course, as the cells are all very close together, indicating that they are very similar. As time goes on, however, the cells spread out and become more diverse, coinciding with further cell differentiation. So the visualization captures the global changes over time, as well as the different branches of the data corresponding to local relationships. With a bit of extra work, we were able to identify the corresponding cell types within the visualization. As another example, we applied FATE to the Frey Faces dataset, which consists of nearly 2,000 frames taken from a video of Brendan Frey making faces in front of a camera. It's fairly low resolution, and the frames are given out of order to FATE without any information about the sequential ordering. Here is the visualization. You can see that FATE captures the sequential ordering without including time as a direct input, which corresponds to the color here. Furthermore, each branch corresponds to different poses, so we can see the local structure of the data. We also see some global structure, as pictures on the left correspond to serious faces, while pictures on the right correspond to smiling faces. If you're interested in seeing a video that traverses the entire data set, you can click on this link here. I also want to briefly highlight some of my work on estimating information theoretic measures. Due to their nature, estimating these measures is a hard problem. Parametric methods may be a poor fit if the model doesn't match the data. Plus, they can be computationally intensive if they require numerical integration. Unfortunately, many standard non-parametric methods have poor mean-squared error convergence. So the solution to all of these that we developed is ensemble estimation. Ensemble estimation works by combining a bunch of weak or poor estimators in a smart way to achieve better performance. For example, you could consider a bunch of k-nearest neighbor plug-in estimators of entropy, where you choose different values of k to get different estimators. You can then take a weighted average of these estimators, where the weights are chosen to minimize the mean-squared error. You can then achieve the parametric mean-squared error rate for sufficiently smooth densities, which is also the minimax rate. The nice thing about this approach is it's quite simple to implement, but it required a lot of theoretical work at the beginning to come up with the appropriate equations for implementation. Given my breadth of work in both methods and applications, I've published in a lot of different venues, including high-impact journals like Nature, Cell, Nature Biotechnology, and Nature Methods. I've also published in a lot of application-specific journals, such as Clinical Immunology and the Journal of Space Weather and Space Climate. I've also published in a lot of machine learning and signal processing conferences throughout the years. If you're interested in these or any of my other projects, you can check out my website and GitHub site for some of the code. Feel free to reach out to me with any questions you may have. Thank you.